So for our last couple of units in this statics class, we're going to be looking at more of the geometry of things as we start building into your future engineering classes. So we're going to be stepping away from looking strictly at forces and how they're affecting things to now the geometry of bodies, and those are going to have consequences down the line for us. And our first topic here is centroids, which is something that we've already seen a little bit of. If we remember back to when we did distributed loads, and we had, say, some loading pattern that looked like this and was represented by the equation Wx. What we were finding then to find the resultant force was finding the centroid. And all that was the integral that we were taking. So now we're going to be looking at a more general form of finding these centroids, right? So the centroid being that x bar value that we were finding to find where the resultant force was acting. So that equation that we had used was x bar is the integral of x w of x dx over the integral of wx dx. So now we're going to take this into a more generalized form for any shape, right? And maybe we want to get even more dimensions. Before we were only looking at the x bar, but maybe we have some shape in space and we want to say what this centroid is in terms of its x bar, y bar, or even if it's 3D, we could even find its z bar, its z centroid. So the more generalized form of this equation is going to be our x bar is the integral of x times dA over the integral of dA. Where in our original one, our wx represented our height here of our shape, and our dx represented the little differential that we were taking. Right, so let me draw maybe like right here. We were taking this little slice that had a width of dx and a height that was equal to this wx term. So our dA was still a dA, this was an area, right? Wx times dx gives us the area of that little rectangle there. And then you're integrating over all of these little rectangles all throughout your distributed load here. So that what we were finding is that this equation is still true, it's just a more specific version of this is what we were using. So now we're going to back it out and say, let's look at more generalized views for more generalized shapes, right? So we have this, and it's the exact same for our y and our z, right? So our y bar would just be the integral of our y dA. And these y's and x's actually have little tildes over them, representing the centroid of each individual rectangle. And we'll kind of break down more what that means with dA. And then if we bring this into 3D, we're not just limited to areas. We can also do this for volumes. So if we brought it into a 3D space, then we would change all of our areas into volumes. So x dv over the integral of dv, right? So z bar dv over the integral of dv. And most critically for this, the real world application of finding all of these centroids, like why would we want to find the center of a shape? Why would I really care? It's typically for center of gravity, center of mass, center of weight, whatever you want to call it. Those are really, really important calculations for us as engineers. We need to know where the center of gravity for things is, especially if you're doing something like, say, a rocket maybe. Say I've got a little rocket here where I need the center of gravity to be at a specific point so that my rocket stays stable, right? I can't have it too high or too low. I need to know where my center of gravity is. And so these calculations are what's going to be used for that. That's typically the application. And these equations can be the exact same as well, right? We don't necessarily have to do it just for the area. It's typically the easiest thing that we can find, but we can also rewrite this equation to be for that x bar, weight, derivative of weight, d weight, things like that, or dm for d mass, right? Change in mass. So there are different applications we can use these equations, but our most general form are going to be these x and y dA integral equation. So let's break down in pictures kind of what that means and how we build that out. So let's say I'm given some amorphous shape like this, right? And we're going to say, this is shaded in, and I want to find the centroid of this shape. And so what I need for my ingredients, right, my x bar is going to be the integral of x tilde dA over the integral of dA, and then the y bar will be integral y tilde dA over integral dA. So how do I find each of these parts? Well, the very first thing I need to do is I need to decide how I'm slicing this. You may recall from Calc 1 or 2, when we take integrals, we're taking these little rectangles, and these are what are giving us our differential, our dx or our dy. So for these, we have two options. We can take the dx path, and if we do that, draw this again, y equals f of x. So I can take a dx differential, and what that means is that I'm taking a slice as I'm going out from the y-axis. So I've got my little width of dx here, and I'll notice my height here is going to be a height of y. Now my centroid of this shape is what I care about. This is what's going to give me the y tilde. So my centroid right here, I need to know the location of the centroid of every little rectangle that I'm taking. And so the way I get that is this distance here, I'm going to call this my x tilde, right? My distance to my centroid of every arbitrary little rectangle. And here I'll notice my x tilde is actually equal to the x distance as I go along through kind of walking on down adjacent, or like walking on down out from the y-axis. So here I'm coming out from the y-axis. My x tilde is just equal to whatever my x value is, right? And then my y tilde, the centroid for this shape, we'll notice is halfway through this rectangle. So here my y tilde is actually y over 2. Y over 2. And I have some y function in terms of f of x that they give me to define this so that I can put everything in terms of the same variable. So here my y tilde, my y centroid, is y over 2. And then finally my dA is just going to represent the area of that rectangle. So my dA is going to be its height, we said was y, equals y, and then the width we said was dx. So since I have everything in terms of y's and x's, I know that I want everything in terms of x because of this dx term so that I can integrate it. So I would plug in all of my things that I need. I have some y of f of x, so I would plug in whatever this f of x function is into every y term that I see. So everything is in terms of x. And these are all of the ingredients that I need. The very last thing that I need is what I'm integrating over, right? What I'm integrating through. And that's going to be this distance along the x-axis here, right? From 0 to b. So for my dx, I'm integrating along the x-axis there, out from 0, from y-axis 0, out to as far as my x goes. So I would integrate from 0 to b. So that's one slice we could take. We can also slice it in the y direction. If I draw my little guy out here again, we'll pretend that's the same shape. Y equals f of x, same equation. But now I'm taking a dy, a horizontal slice. We'll pretend that reaches all the way to the end there. This width dy. dy is the case that we're looking at now, where we'll notice that I have a full length here. Right, this full length is x. And now I need to get my centroid. Right, so now instead of move this so that we can kind of, actually let me move this up here. Oops. Alright, move you up there. And then we'll write for comparison our yellow guy, right, our dy. So dy comes out from our x-axis. So from our x-axis, we're going up and we're taking these horizontal rectangles up, all through our function until we get to the top. So now we're integrating from the bottom to the top. So this is a 0 to h. Integrating from 0 to h now. Now how do my x tilde and y tilde and dA all change? Right, so my x tilde, my distance to my centroid, we'll notice is now half of x. So x tilde is x over 2 now. So they've kind of swapped roles, right? X tilde is x over 2. My y tilde, distance to the centroid of that little rectangle, and it's an arbitrary distance, right? It can be taken at any rectangle wherever you put it, horizontal there. That arbitrary y distance, y tilde, is going to be our y value. And then our dA is, of course, the area of this rectangular slice that we're taking. So our dA is going to be x times dy, and that's just length times width of the rectangle. So now you can see everything has kind of become inverted, where now I need everything in terms of dy. So I would need to rearrange this function to instead be x is a function of y that I would be plugging in to my x's here so that I can get everything in terms of dy and then perform the integration. So that's our basic steps for this. It's going to be decide which way you're going to take these differential slices. If you want to do it dx or dy, you know, the horizontal or vertical, that's going to be your step 1. And then we're going to draw that in so that way we can actually pull our centroid information out of it. And finally, we're going to actually do the integrations. So it's a lot to look at just looking at this jumble of letters here, but it'll make a little more sense as we work through an example. So this example asks us to locate the centroid y bar, measured from the x-axis, of a shape that we're already pretty familiar with, right? We have a right triangle here, and it gives us the general form of an equation for a right triangle. And we already know what the centroid of this is, right? We had this memorized back when we did distributed loads, that it's 1/3 of the way in from the tallest side. But this is going to act kind of like a proof for that, right? So this is where this comes from. And they already give us a differential to work with here. So it tells us that we're going to be using this little dy rectangular segment. So it's up to us just to find the pieces that we need to pull out from this segment and do our integrals. So I'm going to write out our equation. This is what we need. Our y bar is the integral of y tilde dA over the integral of dA. So the pieces of information that we need here, right, we're going to pull them off of the centroid of our little differential rectangle here. So I see that my x centroid is halfway through my x, right? It's a rectangle, so it's going to be half of that. So my x tilde is x over 2. My y height here, y tilde, is going to just be the y height. So that's easy enough. And what else am I missing? My thing I'm integrating over and my dA. So my dA is the area of that rectangle, which is this x times dy. So dA is x times dy. And then that last piece I'm missing, what I'm integrating over is this entire height along here, right? The one that goes along with the dy differential goes from 0 to h. So I have my pieces that I need, right? If I start plugging things in, y bar is the integral from 0 to h. My y tilde equals y. So I have y in there. My dA, I know, is x times dy. And then my bottom integral here, 0 to h, and then my dA again is x dy. Now you'll see the only problem that I have in here is my x, right? I don't know what x is. I can't integrate an x. I need to convert it over to a y. But luckily I have this equation that they gave me that I can rearrange to get x in terms of y and substitute that in so I can actually perform this integral. Right, so if I have this y equals h over b times b minus x, if I do a little algebra to rearrange this, I get my x is b minus by over h. So it's not going to be the funnest integral that we're going to have to do because I'm going to have to substitute this into my x's on the top and bottom here. Right, so my y bar full equation now is the integral from 0 to h, y times b minus by over h times dy all over the integral from 0 to h, b minus by over h dy. And that's my full integral. And it's not, it's not the best looking integral we've ever seen. I'm going to have to multiply some things out to actually evaluate this thing. But I'll do evaluate the top and the bottom. And when I do that integral, I get... I need to make some room here. Let's see, I get by squared over 2 minus by cubed over 3h. Needs to be evaluated from 0 to h all over by minus by squared over 2h. So I did skip a couple steps in my integration to actually get here. But this is what you get when you perform the integral, and then when we actually do the simplification, plugging in our h's and our zeros, what we're going to get is that our y bar is 1 over 3h, right? So 1/3 h, which is exactly what we expect it to be, right? We learned that it happens 1/3 of the way in from the longest side. And so this is exactly what we expect our answer to be. This is where we get that derivation. For any right triangle, it's 1/3 h because all of our b's cancel out, right? So none of those matter, and it's just 1/3 h. So let's take a look at another example where we're going to look at both the dx and the dy and how actually picking this differential yourself, picking how you make those slices yourself, can really affect how easy or how hard the integral that you're doing is. So in this example, now I want to find both the x bar and y bar centroid for this shaded shape that I have over on the left side, which is made up by the equation y equals x squared. So I have this parabola, and the shaded portion is the portion underneath that parabola. So again, my first step is that I have to choose the differential. And I have two options here, right? So I can slice it horizontally, or I can slice it vertically, right? I have these two options. So let's take a look at each of those and how those change the integral setup that I'm doing. So let's look at this one first. If I were to do this horizontal one first, say you really like that dy here. So here I have my dy, but this distance here, we'll notice this is not actually x, that is the length of this bar, right? Our x length is actually this distance to where this equation hits. This is our x length here. So what does that make this distance, right? This full distance is from 0 to 1, which would make this distance 1 minus x. We can already see we might be getting into something hairy if we start taking this dy as a thing of interest, right? Because what does that make the centroid for this? My y tilde and x tilde components, right? My y tilde is still going to be just my y, right? This height here is still just y. However, this distance here to my centroid is if I start at the left side, this distance to my centroid is now the x distance here, right? This x distance plus half of this rectangular distance. So plus 1 minus x over 2, 1/2 of that 1 minus x term. So that's what my x tilde is, my distance to my centroid, which already I know is going to give me some really unpleasant looking integrals, right? If I set this up, and of course my dA is going to be this area of this rectangle, so that is 1 minus x times dy. So let's just set up the x bar equation and see what that looks like. X bar would be my integral x tilde over dA. So I would get the integral going from 0 to 1, right? It looks like both of my integrals are going to be 0 to 1 here. So from 0 to 1 for my x tilde is going to be x plus 1 minus x over 2. And then multiplying by dA. So my dA is 1 minus x times dy. And so I've run off the screen here a little bit, but I can pretty clearly see that this is going to be a nightmare to integrate because everything needs to be put in terms of dy. Right? This is only the top half. I haven't even done the bottom half. If I put everything in terms of y, my x equals the square root of y, just rearranging this equation. I get the integral from 0 to 1 of the square root of y plus 1 minus square root y over 2 times 1 minus square root y dy, and then that's all over 0 to 1, 1 minus square root y dy. What a nasty looking integral. I don't want to do that integral. So let's go ahead and look at our other differential to see if maybe that's something a little bit cleaner, a little bit easier, because this is really quite a monster of an integral, of two integrals, an integral set that we need to be doing. So let's look at instead, I'm going to get rid of this. If I were to take my differential as, here's my guy, and now I'm taking it here, where this is my dx, and my height is again still y. And if I look at my centroid point here, this distance to my centroid, x tilde, is just going to be x. Ooh, already that feels like a breath of fresh air. But what is my y, right? My y center is also not that bad, right? My y tilde, this height here, is going to be y over 2. Hits halfway through this y portion. Okay, that looks good so far. My dA term is going to be that rectangular area, so y times dx. And then, of course, I'm integrating over 0 to 1. So if I start my x bar, my x centroid is going to be the integral from 0 to 1 of my x tilde, which is x, times dA. And dA in this case is y dx all over integral from 0 to 1 y dx. And of course, again, I know my y is x squared. What a simple, beautiful substitution that is, right? 0 to 1 x times x squared dx over the integral 0 to 1 of x squared dx. That's beautiful, right? Those are such simple integrals in comparison. If I'm integrating only an x cubed term on top and an x squared term on the bottom, I already know I'm going to get an x to the 4th over 4 evaluated from 0 to 1 over x cubed over 3 evaluated from 0 to 1. And so that simplifies down to be 1/4 over 1/3. So my x bar is 0.75. And this didn't give us any units, so let's call this meters. 0.75 meters, right? So much simpler and cleaner. Even if we do the y bar, right? So let's find the y centroid for it now, since it asked for both. If I do my, y bar is the integral from 0 to 1 of now my y tilde, which is y over 2, and then x dy, oh sorry, y dx, y dx over the integral from 0 to 1 y dx. Again, a very simple substitution. Y equals x squared. So from 0 to 1 of x squared over 2 times x squared dx. Just making that substitution. Again, really clean integrals, right? So I'm going to have, when I perform these integrals, I have an x to the 4th over 2. So the integral of that is going to be x to the 5th over 10 from 0 to 1. And that's all over. Again, x cubed over 3 from 0 to 1. Exact same integral on the bottom. So this gives me a y bar value of 1/3. 0.33 meters is our y bar value, right? And again, we do a sanity check on this and we say, okay, this makes sense. Our last step of these is always to do a sanity check. So we say, does y bar equaling 0.33 meters and x bar equaling 0.75 meters make sense to us? And we say, okay, 0.75, that hits, and 1/3, that hits somewhere about here. That totally makes sense for the place the centroid could be, right? So always do a check on these to see if you're getting something that's like, way out here. You're like, ooh, maybe I did the math wrong somewhere, because there's no way that the center of this shape is going to be way out here in space. It would make way more sense that it's right here. So our steps for these are always going to be pick a good differential. It's okay if you need to test both of them like this. Pick the easiest one that's going to be the easiest one for you to work with. Usually that's whichever one is always touching the axis, right? So in this case, our dx bar is always touching this axis, but you'll notice that our dy bar doesn't, right? There's this big empty gap here. That's part of what made the integral so nasty. So try to choose things that are always touching the axis there, and then perform those integrals, and finally do a sanity check. Check and make sure that your answer makes sense. For our last example, we're going to be looking at now a 3D shape. So as you may remember, we said that not only does these centroid equation apply to areas, but we can also use them for volumes and masses, center of weights, and all of those things. So really the main difference when we go from an area to looking at a volume is one, of course, that our equation changes. So this one asks for y bar. So our y bar is our integral of y tilde dv now, dv. But the other main change is that instead of taking rectangular slices, in 3D object we want to take disc-shaped slices. So here I have this ham-looking object, and so what I want to do is I want to take a disc slice. A disc here out of my shape. So here my differential, this width, is dy, and then my disk here is the area of a circle. So I'm still doing a volume, where dv is going to be my dy times the area of this circle here. So in this case, the area of my circle, since this ham shape runs along the y-axis, it gives us this equation of z squared equals 100y. My height is going to be z, which in this case we can treat like the radius, right? This z, and then it circles around the y-axis. So my dv in this case is going to be the area of a circle equation, which is pi r squared, but in this case we'll use z for our r. Pi z squared times dy. So that gives us our dv, and you'll notice that it doesn't ask us for an x centroid or a z centroid, the z bar, x bar. And if we think about it, it's because we already know where those are intuitively. This is a symmetrical shape. It's kind of this like long ham along the y-axis, where the z and the x centroids are on the y-axis, right? They're both 0. We already know what those are, so we don't need to set up equations to solve those, since this is perfectly revolved around. So we really kind of have the major component here that we needed, right? We have our dv, our y, distance y to the centroid of our disk. Y bar is just going to be y. So we can start plugging things into our equation, right? Our integral is over the entire y-axis length here, which is 100 millimeters. So from 0 to 100 of our y tilde is just y. And then our dv is our pi z squared dy. And we'll notice they gave us an equation for z squared here, representing this edge here. So our z squared is 100y, a super easy substitution for us to make here. Right? I can just substitute in 100y. And then my bottom is now just the volume portion, so pi z squared, which I know is 100y, times dy. So simple enough. It's just now the matter of doing that integral, right? So my y bar is going to be, oh, I can take out this 100 pi term from each of these, right? So I just end up with the integral from 0 to 100 of y squared dy over the integral of y dy, which is going to give me y cubed over 3 over y squared over 2, each from 0 to 100. And that gives me my final answer. Y bar is 667 millimeters. 667 millimeters.